All right. What? I'm sorry. All right. I am here. Okay. So I was checking, trying to ascertain, because I forgot yet again to check what the number of ChaDevs meetups that we have hosted so far is, which I think is like 158. So again, 3 years going. Such a great group. Really excited today about our speaker. We do have a few announcements. Obviously, we want to shout out to our sponsors, one of which is brand new and isn't up here yet, but I want to give a shout out to Squid for sponsoring ChaDevs and supporting the community here. Am I missing any other ones that we haven't updated graphics for? Not yet? Not yet. All right. And then we have Richard, who wanted to give a shout out to an upcoming event too.
Yep. Thank you. So next Tuesday night, I will be in the Accelerator space, is our monthly CHA DevOps meetup. And this month, we're going to have Adam Jimerson talking about BSD jails. I got a preview of the presentation last night. It's awesome. It'll show us BSD jails, contrast it to things like Docker and Kubernetes. So if you're interested in all of that, we'll be 6 o'clock Tuesday night over here in the Accelerator space. Thanks.
And Richard should give himself a shout out because he is next week's speaker. Yep. So Richard, we'll be hearing from Richard in a week about Red Hat Cloud Forms. Is that correct? And Azure. Okay, awesome. So today we have a very special speaker all the way from Berlin. We're going to pretend like he flew all the way to Chattanooga just to meet with you guys, and all the way from Berlin, but he may have already been in New York for something else. But we'll keep that secret. So CrateIO is a distributed database that I found over the last year and have been playing with it on a project I've been working on. Community is really great. Klaus has been very helpful in their community Slack channel with questions we've had in our implementation, and we wanted to. I saw them at GrafanaCon in New York in November, and they did a really cool presentation. Definitely the coolest technology vendor presentation that was there, but that may or may not be saying much. But I think that Klaus is going to be showing off some pretty cool stuff today. So with that, we'll turn this over to Klaus.
Thank you. All right. So yes, I will be going SSH but talking about containerized databases in a machine data environment. So yeah, I'm Klaus. So as we've heard, I do a lot of support, and I started off as an integrations developer at Crate.io, I don't know, like 1.5 or 2 years ago, and now I'm doing a lot of other stuff related to outreach, developer relations, things like that. I'm also active on Twitter and doing, posting about Rust, Raspberry Pis, as you can see here. I brought one, and tech in general. And yeah, I included a Twitter handle on the lower left if you want to contact me somehow or have questions about the presentation or Rust or Raspberry Pis or things. Yeah, you can just message me or follow me or whatever. So CrateIO is a company that was founded in 2013 in Dornbirn in Austria, which is a very mountaineering area. So hence all the pictures of nice mountains in the background. And it has expanded to several places since then. So we have an office in San Francisco, and we also have an office in Berlin, where I'm at. And right now we're roughly 25 people, and we are creating a distributed SQL database to do that. In the Docker store, which is our main download source, we have roughly 1 million downloads, or on the Docker Hub, and we're glad about that. So. But first, let's talk about machine data. So machine data is going to be big. That's like what analysts say. And they have predicted it to be large, basically the next form of big data, and it's predicted to be roughly 40 zettabytes. That's 10 to the power of 21 bytes by 2020, and basically the growth rate between 2015 and 2020 will be around 5 times what the growth rate between 2010 and 2015 was. So it's going to be huge. But it's also, machine data has other characteristics too. It's also always a high insert rate. So you read something from a sensor like that, and you insert it in a database. So you have millions of inserts per second easily. But also the data changes a lot. So you have different sensors or sensors that get replaced. You add sensors, and they have different form of output in really any form that you can imagine, so including blobs. And with that data, you want to have two things essentially. Real-time query performance. So, your temperature data should tell you what the temperature is now, not in 5 hours. When, for example, your house is burning down, you want to know as timely as possible. And then, but at the same time, you want to maybe include all the history or some parts of the history in your queries in order to find out if something is slowly heating up or slowly dying or things like that are happening. So you have this, you have these two query characteristics you wanna be able to achieve. And on top of that, the data grows usually quite easily and exponentially. So just adding, increasing the frequency of reads on a sensor would just exponentially explode the amounts of data and the amounts of inserts you have. So examples for machine data applications are usually also quite well known. It's of course the Internet of Things. So it's like from egg trays over fridges to anything that has nowadays internet connection, but also wearables of any kind, so fitness trackers and things like that. But but also more professional applications like like data center monitoring, log analytics, and anything that produces a nice chart. But also Industry 4.0 applications, so anything from automating your production line, but also to placing sensors all around the factory plant in order to get data, what was previously done by humans, for example. And that same applies also to vehicles. You can also track your vehicle data in all kinds of ways in order to get some health data, for example. So we have users doing that. One of them is ClickDrive.io. They do exactly that. They do fleet management and vehicle tracking. So they have 2,000 data points per car per second that they analyze, and with that data they can do some they can just tell the customer that their car is breaking down or is gonna be breaking down soon. Or that there is, the efficiency with the driving efficiency is not great and it could be better, or that it's like there's some accident happened and they can reconstruct the accident just from the amount of sensor data they have on that. Something similar is the same thing basically for apartments, and that's, by the way, not a spelling mistake. So their logo is a bit different. So it's not for kangaroos; it's for apartment. And they basically, they place a sensor in hotel rooms, for example, and they can figure out if there's, a noise, if there's gonna be a noise complaint before the actual complaint happens, because they know when you're being loud and annoying there. Or they have alerts based on the data before something, they can prevent things there. And Skyha Networks does something similar. They do the security, cloud access security broker, which is a fancy term for they monitor your login behavior and do some unsupervised learning on top of that to figure out basically a baseline where this like you log in AWS in the morning and log out in the evening or something, and then all of a sudden something in a completely different country at night something is happening, then it's likely to be maybe a malicious, some kind of malicious intent or some intrusion that's going on. So they can tell you that. And they get billions of events a day from all kinds of different cloud vendors and anything basically you can log into. And the security has security elements. So this has all of these large data volumes and inserts and all that has led to a very dominant architecture in the last few years, and that has also been proven to work, and that is of course microservices. And microservices are basically they are small units of services that make up your ultimate service in the end. So you have basically a compound of services working together to provide that. That gives you some flexibility in terms of deployment, and you can also scale very nicely horizontally. So you can add containers, for example, if you do that, and add more of them in order to handle more load, right? So the only thing that's usually a bit troubling is databases, and that's what we're going to talk about a bit. So I wanna talk about basically an open stack as an example there. So the companies I've been talking about earlier, they all have roughly the same structure, how they do their business basically. So they have a sensor that produces data, then they have some kind of consumer application that enriches the data, that does some production, or basically some processing on it, and then it ultimately stores it somewhere in a database. And then you have a visualizer that takes this data and draws it, makes nice charts, and does basically shows it to someone. This could easily also be something more sophisticated, like some kind of machine learning structure or some kind of AI or something like that. But let's go for a visualizer for now. So the way this is usually deployed is you take a load balancer, and then you take this consumer, and so here it's abbreviated as C as consumer and visualizer, and sensor and user. So basically you take these containers, these white boxes, and deploy them on physical machines or virtual machines, which would be one of these stacks. You take 3 of those, and then you can easily achieve high availability. It's like this is an easy way of doing that. And in order to route requests between them, you use a load balancer in order to do basically play a reverse proxy and add maybe some encryption on top of it. And then the sensors can fire basically data at the load balancer endpoint, and that figures out where it should go. And the same thing, the user can also go to that, and it's depending on the configuration, it can see what the visualizer is showing him. However, there's something missing here, and that's the whole data storage. And if we add that, it gets a lot more complicated. And specifically, a pattern that we've seen is very common is like you have a SQL database, because that combines decades of knowledge on rigid storage, and has a nice query language on top. And it's usually supported by some kind of NoSQL database, because SQL databases usually can't do everything. They can't do search, for example, sometimes very well. Or they have trouble with very unstructured data that changes a lot and maybe needs some pre-processing, or are just quite, they have an upper boundary on scaling. And in order to keep them synchronous, it's usually done with the message queue, that you insert something into the message queue, and that these databases are basically the consumers of whatever comes out of it. So this is also called Lambda Architecture, if you want to look that up. So basically what this results in is that every consumer would insert into the message queue, right? And then it gets propagated, and in order for the visualizer to show whatever data has been inserted, it needs a connection. So every visualizer needs a connection in the backend for both of those data storage layers there. And yeah, so this is basically what a lot of deployments look like. However, there's some problems usually with that. So essentially, first of all, you have a lot of network connections between those two systems, essentially. You have a message queue. You rely a lot on a message queue to do stuff, but as soon as that message queue is down, basically everything intermediate in there is gone. They have been known to lose data, especially if you scale up. And and the main thing is you can't scale up really well. So what happens if you have more users? You can probably deploy more of those stacks easily. So you can just add another virtual machine, deploy another set of containers there, and then you can handle the consumer and the visualizer part easily. However, it's quite hard to scale up the SQL database. You can literally see how far you can scale by the biggest instance you can buy. And then later, basically after that, it gets very complicated to do some sharding on the Postgres database, for example. And then the effort grows and it gets more and more expensive. The NoSQL database, on the other hand, is known to be very easy to scale, but however, it's another set of instances that grows with somewhat related to the load it takes in. So, this creates, all in all, this creates more instances. So you have access control issues. You also have a data duplication. So you have everything in the queue, but and you still need to lock down your SQL database, but then you would also need to lock down your queue. So this gets complicated in all kinds of ways there. And it has a very single point of failure. It has a few points of failure there, including specifically the network and the message queue and things like that. So we have identified basically what could solve the problem, which would be like a native citizen database, and that scales with basically with that, with your setup and with your instances. And that would need it to have a few capabilities. So it has to have basically a shared nothing architecture in a way that it doesn't introduce states between them. You have to have some kind of native replication and some sane defaults that you can just use. Otherwise, you replace ops management with configuration management, and that's also not really great. You have to have some resiliency, of course, because it's a database, and it should be cross-functional in order to not add technology, but rather replace it or replace stuff and cut it down. So you would ask yourself, is it another database? And yeah, but which one? And yeah, we have made our own. It's called CrateDB, and it's on GitHub. It's an open source database. You can also get it on a Docker Hub, and it's a distributed SQL database. And we also have fans in the Docker community, so they were very excited about our 1.0 release in December. CrateDB is essentially that. So what we imagine a good database and a good container citizen should do. So it has a shared nothing architecture. It has partitioning and sharding built in automatically. It does replication. It has some, it requires 3 configuration settings to be set on start. And it handles, basically it handles unstructured and structured data really well, and offers all of that in SQL. So the fundamentals are that it stores everything on disk. So it's disk-based indexes that utilize caching to get to the speed of an in-memory database or a columnar storage essentially. So these units of data that are stored on disks are called shards, And in order by distributing those shards, it can push down the queries to wherever the data is located in order to have distributed execution. So shards, more shards equal more concurrency if you have the node, the nodes to back that up. And from a bird's eye view, this could look like that. So you have some kind of client connecting to either of those nodes in this 3-node cluster here. And since they have shared nothing, they all basically look the same, and you can connect to all of them via either Postgres or HTTP. And they all can parse the query, plan the execution, and have the other nodes, basically poke the other nodes and get them to return data to it. And yeah, this basically distributed execution engine that we made. We use Elasticsearch for clustering underneath, and we use Lucene basically to store the records on disk. So this is basically what the better setup in this case would look like then. We could remove most of the moving parts. So we could cut down and reduce the stack, which is usually a good idea because less is more in that case. And then you also have reduced network connections, because what essentially is required is each database to talk to the other nodes so that they can form a cluster and they can work together. As soon as that happens, you only have each consumer to talk to basically the local host instance, and each visualizer do the same, because then you have you reduce the network traffic between the nodes, and that makes it, first of all, it removes a big point of failure there. And then you can just add more nodes. If there's more load, you can just add more nodes, and they will find and rebuild the cluster as you go, and it will be, larger cluster can handle more data and not more concurrent queries, and a smaller cluster can handle less. And the same goes probably for the microservices that the database backs up. It also lets you do some live reporting, so you can tap into the database and just run SQL queries and find out what's happening. And it offers, of course, the flexibility of changing the schema anytime, basically, they want. So which is, for example, usually quite often is useful in development, and leads also to a lot of people having having typos as column names, because it's almost too easy sometimes. So yeah, as I said, this removes the single point of failure. It reduces network traffic. You have no queuing system, and database is isolated, which, as we have seen in the last weeks with MongoDB and Elasticsearch instances, is a good idea not to expose them to the outside world. So let me show you that all the things. But first of all, what I'm going to show you is a demo with my Raspberry Pi here. So this is a Raspberry Pi Zero. I'm going to plug it in right now, so it boots and it starts inserting data. It runs a Docker container that essentially gets the data in a 100 millisecond interval from this BMP 180 temperature sensor that is connected via I2C on the Raspberry Pi. And it starts inserting data into basically a load balanced cloud instance that we run on Packet. So in this case, this is all, this is internet connection sharing on the MacBook. But it could do that with the Wi-Fi as well. This is, and then it inserts it into something called Eden Server, which is a random name I made up for my project there, which is an API, a RESTful API that just collects the data and inserts it into the database and does some authentication, of course, and and makes sure that the data is right. And then it's inserting into Crate, and we use Grafana as a G here as a visualizer. So I have deployed already 3 nodes on a hoster called Packet, and each of them has either one Eden instance and one Crate instance running on them, and we can connect to the Grafana instance to show stuff. So I'm gonna show you that. So first of all, I deployed it using a Docker file and Docker Swarm. So this is Docker Swarm 1.13 can have Docker Compose version 3, which lets you define services and run in a swarm, which is quite nice to do things with. It deploys 3 services in this case. One of them is the database, so CrateDB. It pulls the image from the Docker Hub. Sets the heap size to 3 gigabytes, it should usually be the half of the limit of the Docker container, so it utilizes caching properly and gives it some space. This is the run command here, and this, as you can see, these are the configuration options that are required to run basically a 3-node crate cluster. So there are 3 expected nodes. So it knows when the cluster is full, is basically what it's supposed to be. It has recovery after nodes and minimum master nodes. It's 2, which is basically a quorum. So it doesn't form 2 clusters if you have, for example, 4 nodes and then you have 2 nodes on each side, which would be bad. So you have a quorum of 3, so they don't form basically 2 clusters, and each of them thinks they're the main cluster, called split brain scenario. Then we disable multicast because it doesn't work on the Docker network. Instead, we enable unicast, and this is basically a nice way how the Docker service works. It utilizes DNS round robin with this DNS address, so they can ping each other there. We'll also bind on specific Ethernet and call the cluster NYC here. We attach 2 network connections there. So one network for the Crate nodes to talk to each other, and one client network for each client to talk to a Crate node. Then we mount a volume, so we don't write data into the Docker container, and we deploy it in a global mode, which means 1 instance per, or 1 container per instance, essentially. The placement constraints is here now node role is manager, but that's a lazy way of making it work with labels. So in a real environment, you should use labels properly. Then we deploy Grafana. Grafana is a nice dashboard building application, and it can we can chart things very easily. I will show you that in a minute. Use their official Docker image, forward the ports, attach it to the client network, install the Crate data source, do some mapping, and again, or similarly, actually, it's a replicated mode, so we can control how many replicas we have there, and here again, the placement only on the manager. And here we have the Eden server. So this is something that is hosted on my Docker Hub profile thing. And it starts after CrateDB. It's also attached to the network, and it has some other port forwardings here. We have a configuration file that we pass in for this, and they also use this also uses global mode because we want to have that on every node that we deploy, and the manager constraint. And this would be a nice thing if it worked properly, but you could actually add the Raspberry Pi to a swarm and then deploy the same thing on the swarm as, on the Raspberry Pi. Basically use one file to deploy everything, including the sensor reading container. And then we add a network, the networks here, and so when it's done, it looks like that. There are three services deployed. They run, basically each of them have 3 replicas because it's 3 nodes. And that's what they look like. There are 3 nodes in there. They're all reachable, and I also promoted all of them to managers so that they can run the actual application. So the thing should have booted, so I can look at that. So this is our admin UI. We now use localhost because I do SSH port forwarding into the cluster, onto one of the machines. And these are the 3 machines that are deployed. So we have created a table here. This table is getting inserted into. And yeah, it has, since it's not running for a long time, it only has 62,000 records in there, and it utilizes partitioning in order, which is, so yeah, you've seen as inserts going on. It utilizes partitioning, which essentially lets create a table every month. In this case, it's every month because I use the monthly partitioning, but it creates a table every month of the data for it. Then it can have easy time series. Like it makes organizational aspects of the time series easier to handle. Then we support something like objects, or called objects here. So these are objects, and this sensor does temperature and air pressure. And in this case, I've used a schema for like that. So it is an object that inserts basically for each sensor type a unit and a value object basically. And if I had a luminosity sensor, I would have another column that I can just add that has luminosity and value and unit maybe, and things like that, and gain and yeah. So settings I could also add there. And this is basically the way to show the paths, or to symbolize the path, with the agent being the Raspberry Pi, the name being the name of the sensor, and the role that it is a sensor at all. And month and timestamp. So a month is actually a generated column from the timestamp column. So it takes a timestamp and truncates it to a month. And then it changes every month, and that gives the database the ability to create a new table, essentially. And that's actually transparent, so it's you still would query that table. So with Grafana attached to the top of that, we see that it looks like that. So we can just maybe scale it down. So it does a query every 5 seconds. And now we show the last 30 minutes, which is a bit long. We can go for the last 15 minutes. And since there's not a lot of data, the querying is also quite fast, but it stays also really fast, since a 3-node cluster can handle quite a lot of queries there. So we can just zoom in. So the data is actually recorded in 100 milliseconds interval. So we have now an over, basically, we have to somehow average them across a minute, but we could also use seconds, for example, then it would change that. And these are all always live queries. Every time there's something small turning progress indicator on the top right, it does something. It could also do different methods there. So yeah, we want basically, so it's inserting data. So we can look at the last minutes to seconds maybe. So as you can see, there's it's a bit weird because it's a very fine scale. And it's also the Celsius, of course. So yeah, it's 21 degrees in here, and if we hold it or we put it closer to my MacBook, I can, temperature does weird things like drop, or not sure why it dropped. Yeah, I was doing some stuff yesterday, and I put it on my MacBook. this morning, and as you can see that there's, so first of all, Grafana connects those 2 points. But as you can see, the MacBook has been quite hot for that time, and it does some, produces some interesting graphs. So as it is still inserting data, it refreshes only every 5 seconds, but we can just shoot, and I promise that it's going to be very resilient. I can just turn off a node. So on the right, I'm just here now basically stopping Docker on one of the nodes, so it would lose the swarm connection. I did that right. And then we should see that there's, so basically crate will tell you that now your replication, so we have 1 replica on this table, so it will tell you there's something wrong with your cluster. And it is true, because it lost 1 node. And then it starts replicating again. So there's a percentage somewhere. Here is a recovery percentage that will go, now since we have still 2 nodes, it will still start to replicate across the 2 nodes. If we had 2 replicas, that would make it 3 copies. It wouldn't place 3 copies on only 2 nodes, because that doesn't make any sense. So it would just stay in that, in this case. So, and also it will tell you that something is wrong with your cluster. So your expected nodes is lower than the actual nodes there. And we will still see that the inserting continues, and that there's basically, that the sensor didn't really notice any difference there. So, so I also do that basically in that same application I use basically for my home. And if it was working, I would show you that. Basically, but yeah, I have like 10 million records over the last, basically from a temperature sensor that is in my living room. I'm not sure. This is a very fancy browser. So no, it just, I don't know. Yeah, it just shows this for some. So yeah, this, what I just showed you is basically a nice open stack for machine data, we think, and especially I think, and it lets you do analysis with SQL, ad hoc analysis, so we can run queries afterwards if you want. It's just, it integrates well with SQL-based tools that are already there, so there's not much rewriting going on, and actually you can use the Postgres driver to some extent because you speak the same protocol, and it's horizontally scalable, so you can add and remove nodes, and it just will adapt. So that's it. Thank you for your attention. You can basically ask questions, and these are some links. There's my GitHub profile, Crate's GitHub profile, the Docker, our Docker profile there, our Docker Hub presence, and yeah, Twitter accounts, and our website.
Questions?
Yes.
A little bit confused. When you kill that other instance, you started replicating?
It started re-replicating. So now we have, it finished that, so it has now 1 replica. So there's, you have a constraint that there's always has to be 1 replica of the data. And if that replica is gone or is partially gone for some reason, like the node went down, then then the constraint is not satisfied anymore. Then you need your replica back, because the next time something goes wrong, you wouldn't have a replica. And it's basically just talking about the data there, and then it starts to basically fill up whatever is missing from that replica in this case, and then it starts, so it gets it back to green table status again, so that we have, you could, in theory, now lose another node. And in a bigger cluster, this makes more sense. A 3-node cluster can't lose 2 nodes, but in a 10-node cluster, you could lose 2 nodes after each other, and that, then it would still work fine. It would start to rework that basically.
But if you bring the one that you just killed, if you're coming in through this load balancer, how does a load balancer know which one has the latest or the up-to-date database?
The cluster will figure that out itself. So this is what the settings are for, essentially. So if the settings tell it, go and look for another node, go and look for the others first before you start declaring your own truth, essentially. And then it goes out to the other nodes, in this case to the remaining 2, finds that they have a newer state, and then it starts to pulling in their cluster state and basically their tables, their data, and starts comparing what the node has at the moment and what it should have. And the load balancer in this case only knows that there is another node, and the node itself will, if it gets a query, it will just forward it to the others. Basically, there will be no stale replicas in this case because it's only one, and it starts instantly to freshen up the knowledge about the cluster state.
Is CrateIO built on? Does it build its own clustering algorithms, or is it built upon other projects? And if so, what are they?
It's built, so specifically the clustering is built on Elasticsearch's homegrown algorithm. So yeah, I think they have built it themselves. It's not yet Raft. It might be. We hope that we can get there by the end of the year and implement Raft instead.
Are there any provisions for handling, for stopping the propagation and replication of corrupted data?
So it's very picky with corrupted data. It will just show you an error, essentially, and then you have to handle it yourself. So I'm not sure if you even can insert, but I think you can insert in that data and you can select something, but it will specifically if you have if you have a lot more partitions, it will tell you this partition has missing shards, and this is something went wrong here, and it will not include this data in queries mostly. But you have to fix it yourself.
In our system, we're using 2 databases locations, right? So one is a primary, and we back everything up to a secondary, not for performance purposes, because we don't have huge amounts of data, but for backup purposes. Could this system replace our way to back up? We essentially use a Postgres as like a parent and a child type of relationship where one is a slave to the other, basically.
Yes, it could, in a way that you can have one cluster and maybe have 2 availability zones on AWS, for example, and then this is a config setting that you can set, like this is zone A, zone B, and then it always will place one replica into the other zone automatically. So, but they still will work together as one cluster, and they will just look like that, with probably more nodes, but under the hood, they will always use basically this type of replication, that they always will move one replica in the other availability zone with the other label in this case. So yeah, it's not strictly that you have that and that, but you have like one, and then it takes a sort of care of that in itself.
All right. Thanks so much, Klaus. It was a great talk. It's always cool to see a live demo that works, even if the temperatures are inverted, you know. So thanks so much, and we'll see you all next week with Richard and Red Hat Cloud Forms and Azure. So thanks so much, everybody.